Okay, thank you to be here for this lecture, which we will see together as one of two exercises, which how possible to say can be seen also as possible exercises or similar exercises for the examination. Okay, let me go to or the switch to the lateral camera. Again, this nice picture. I don't know if it's nice, but anyway, it's in the picture. In the exam, what I will give you directly the transfer function. Why that? Because if you remember, we did or we analyzed the modeling, also this model here, in the course of dynamical systems. This means I don't have to check. You don't care about the model. I will give you directly the transfer function. About the transfer function, I told you a lot. You remember the transfer function, just to give you a parallel example. The transfer function which consider in output the position, we called x of s divided f of s. I mean, the input is always the force, and the output in the other case was the position. It's quite similar to this one. Now, I will start with the similarity because basically position control and velocity control for such a system, please pay attention, and then I will clarify why I'm saying for such a system. The approach is the same, and the control loop, GOL, is exactly the same. Of course, the control is different. What is the difference? If you remember, x of s divided f of s, let me say position control, is characterized by parenthesis, and I multiply by s. Should I come back to the lecture of last time? But believe me, no? We will come back later. You remember this, but it's easy to see. It's easy to see because this is connected, let me say, with the concept that the velocity, or better to say, the position is the integral of the velocity. This we agree this. This means, think about here, probably for comfort. V of s, excuse me, V of s is equal this transfer function multiply f of s. Did you agree? But if you think here that the velocity is the integral of the, the position is the integral of the velocity, this means that if I write here x of s, it is enough to integrate this expression here, because this expression here, this divided this multiply f of s, is the velocity. Of course, in Laplace domain and so on. I don't know if can help this. V of s is this expression here multiply f of s. This means this expression on the right is exactly the velocity. Now, if I want to transform everything, if I want to see what the position is this expression here. Think about f of s, multiply f of s, divided s. Why that? Because if I divide it by s, I have an integral, no? And then you remember the integral theorem. You remember the derivative is represented, reflected by multiplication by s, and the integral is reflected in s domain by division by s. Now, think about that. It's not necessary to learn this for the exam, but can help in order to understand that if I give you a velocity control, if I give you an or in a position control, now we can understand that really change a few things. We will see a little bit in detail, in particular in connection with the controller, which I would like to show you, or I would like to implement. Okay, in the exam I will give you some data in order to be clear what we have or what we don't have. Basically, the mass of the car, this friction parameter, yeah, this because of the wind, because of the friction on the road, because of the friction on the axis of the wheel, really roughly uh, model. Do you remember I told you that friction is a big topic, no? But for us, it's important to understand that there is the factor which takes into consideration mechanical losses, but we don't consider in detail this phenomenon because this phenomenon is strongly nonlinear. Do you remember Coulomb friction, Lugre friction? It's extremely complicated. Tribology, there is chairs, layers tool in tribology. For us, in this exam is in a linear model. The linear model is basically collapses in this B here. Okay, question one. Look, let's consider the following regulator. We have seen just this form of regulator, which is the basic one, which is one of the most used one, is in a controller in which which can represent also in its simplification. When I simplified a little bit, and the PID, do you remember? This is very important in automation. But allows me to show you also some properties, some characteristics. I would like to say basic knowledge on Bode diagrams, or methods based on Bode diagrams, method based on the Bode theorem. Do you remember I told you the Bode theorem, what I presented shows many limitations. Probably next week I will tell you very quickly about the Nyquist theorem. Probably Maren told you about the Nyquist theorem. The Nyquist diagrams. Tammo, did you do the main controller? No? Did you hear about Nyquist theorem, Nyquist diagrams?
No,
Did
not yet
okay.
from Prof.
That doesn't matter. I will tell you very quickly next week when we discuss question because with the Nyquist theorem, Nyquist methods, we remove some hypotheses of the both, yeah, both theorem, both diagram, both methods. But I don't have time. But anyway, if you come to me or bachelor thesis, typically we are working here more in nonlinear methods, but we can also consider this. Okay, this is the controller which you can find also in the data sheet, in the test, in the data sheet. Until here, don't care about to keep in mind anything. Now, we can understand that at the end, the method is the same. It doesn't matter if I control velocity or position for this system. Please pay attention, for this system. Why that? Because you remember one of the question which I have is here. Oh, let me show you everything. Let's go. The first question is articulated defining the controller, which is always the same, Ki divided S up to H, multiply C of S, something which we will define later. The first question is to calculate the minimal value of H, this exponent of the integral, such that, yeah, that the steady state error equals 0 in case at the end I wrote this a little bit confused, but it's written here. Basically, what I want. Basically, I want to have an error at steady state error equals 0 if I apply a step, an input, assuming this control scheme, always the same control scheme. This means I would like to reach steady state, we can see here 10 meter per second. This is the velocity, the goal of my control. At this moment is the unique specification, which allows to calculate h. h0, h1, we start for h0, h1, basically the final velocity. What I specify at the beginning is the final velocity. This specification or this challenge can be reached, can be obtained just, I would like to say, steady state, just calculated this h, the exponent of the integral. Could be an integral, could be two integral, could be two integral actions, could be no integral actions. Then we will see mathematically. We will see mathematically. And then we will come back to my preamble, why I told you between position and velocity, we have an integral, or better to say between velocity and position. It's better for this system. Excuse me a little bit. Here. Question here. We are here to learn, not only for the exam, or better to say, to learn for the exam. It's okay what I specified. The question is clear. Until now, we don't have to do anything, just in the exam, just to read the text. In fact, we don't have calculations now. Understand the text. The idea is, given this structure of a control system, extremely important is, given my task, you remember I told you that the task is to control the velocity. Otherwise, why I put in the transfer function between velocity and force? If the goal is to control the position, of course, the transfer function is between position and force. The idea is, which kind of force I have to generate in order to obtain goals? Which kind of force I have to generate in order to obtain goals? This means RV, or better to say, V of S, or the V of T at the end V of T, equal R of T. What is R of T? It's the value. I would like to achieve at this moment 10 meters per second. Then the second question will be, this is if you were a little bit expert in autos, but how many seconds I have to consider in order to attain 10 meters per second as final velocity? If I need 1 hour, no, this is not the problem for the controller. If I need 1 second, of course, you have to push a little bit more. This should be the second question. But now, to calculate h, we will come back to the concept of an integral in the control loop. Why that? Because the control loop consists of the controller, you remember, the product of the controller and the product between the product between the controller and this one. You remember the control loop GOL is GR multiplied GSV. Problem formulation is clear, no? We are speaking about a controller which will achieve the goal in infinite time. In infinite time. Student asked me, but this is something theoretical. This is something I would like to be happy, as I told you today, not in infinite time. I would like to happy in the mean to achieve the goal. No? Even though you remember this interesting, and student asked me why the goal to put goal to have goals is in the disturbance. You remember in the slides we have a scene question. It's a little bit confused, I know, because was directly in the discussion. But it's not, we can understand, with, no? If you look at the scheme, this means the error 0 at time infinite. This means the difference between the goal, reference signal, the reference signal R is our goal. And this is what we have. This means if the error somewhere, we hope that not in infinite time, but in finite time, will be zero. Of course, this means that I achieve my velocity. This kind of controller in this specific model will achieve the goal in infinite time. But also this controller can achieve the goal in finite time. Of course, if we model the system in more real form. Look at this example. No, I told you many times. We can see that we stop. It seems that we stop in finite time. But the reason is we have a friction, which is, we don't model correctly the friction. We don't model correctly the friction. Static friction, remember, in Germany, after arrival, there is a point at which you cannot proceed. But forget this. Calculations. Please pay attention here, S here, and what I told you before about the S here. Now, you can find also in the data sheet in the form example, this theorem here, which allows to calculate everything in S. You remember, S is an extremely important domain, which can really simplify our life. I mean, our life, the examination. When we do a transformation, when we do no, I forgot to say why the goal is in disturbance. Just again a little bit. This is nice because I receive a request. You remember when we have a disturbance here, if you look at the past lecture, I can calculate the transfer function between the disturbance and the output. Look at I don't have time to show you again, but just conceptually, I can calculate the transfer function between the disturbance and the answer. Disturbance and velocity. I have a slope, I have a lower. If you look at the transfer function between input and error, the transfer function is the same as the disturbance and the output. In this sense, we say that the goal acts on the control loop as a disturbance. Philosophically, now, if we don't have the goal to pass the exam, you don't have to come here. This means the goal disturb you. For instance, disturb you tomorrow or today because you wake up early, waiting for me that I will with my delay. The goal is always in disturbance. I mean, the best way to don't accept disturbance is don't have a goal. If you don't have a goal in the life, you have to sleep. Right. Goal are disturbance in this sense. If you look again in the lecture, we can see this concept also in mathematical sense, in accordance with the transfer function which I recalled today. Now, you can find this in my study, my study also, in the data sheet, in the form example. Now, what we can do in the exam to answer the question. This transfer function here is exactly what I told you exactly now, is the transfer function between the reference signal and the error. You can find also this in the data sheet. If you look, did you have a data sheet from my study? Yeah, you can find also this expression. Is there. This means the error E of S is the transfer function multiply R of RV, because this transfer function is E of S divided RV. RV is our disturbance, the cause, what moves us, what generates the error. Each goal generates an error. This is the error. We have a comment here. And then this S here came from the theorem. The theorem, I demonstrated also the theorem. I don't know if you remember. I demonstrated also. We don't need for the exam to learn the theorem, but in the lecture, I needed to show you at least where this example of this theorem come from. Huh? What this result, better to say, or you can say which this theorem come from. Okay, now calculations. Really, we will proceed with algebraic calculations. I replace GR with the definition of the controller. Again, some students ask me, what is about the controller? What is a controller? The controller is a function of an error. In the control loop, the controller is a function of an error. This means I generate, in our specific case, an force. We try to minimize, we try to obtain the error 0, in our case, in infinite time, producing a force. Now, from here to here, I plug it in the definition of my controller which you want to apply. How many controllers I have? Infinite up to infinite. You can dream a controller in the night. Very important is the function of the error. We generate the input of the system. Of course, this about the effectiveness of the controller. If you dream a controller, then we have to discuss. And this we will see also a little bit also in this lecture. No? This is a very important controller because we can solve many problems, and we can end up in the PID, PI controller, which basically we can buy directly in the chip, and so on. And you can tune with a parameter. Now, the question was calculate the minimal age. No? Why that? Well, believe me, to realize integrals costs. It costs. Not only costs because, okay, what is 50 cents in the chip? But you have to consider that in the production, we are here to learn. So production, we produce, I don't know, 1,000 chips per day. 1,000. I am not good in math. To calculate how many money, something like that. But not only this, it's not cheap or is expensive in terms of control. I mean, including if we need to control a system more and more integral, the performance of the controller is not so let me say not so good. I mean, a controller which need an integral is more problematic, let me say, so with respect to a controller which don't need an integral. Now, in this case, we cannot see very well, but think about this concept here. If we can avoid controller, is always something which should be considered. Therefore, the question is the minimal age. The minimal age means the minimal number of integrals. Now, you remember the transfer function of a constant, or the step, better to say, is 1 divided s if the amplitude is 10. Also, this one you can find in the data sheet or directly in the exam test. This means you don't have to remember. I'm not in a good position. You don't have to remember the exactly, but at least the step in the ramp just for the day of the examination. I would like to learn. But in any case, I think there is also a table with the, I put what you need, because if you don't remember, this does not mean that you are not able to do the exercise. It's just you don't remember. I will put in any case the transfer function, the Laplace transform, the Laplace transform of the signal which we have to consider. Now, calculations. You can see S and S I can cancel. H equals 0 means basically we have a 1. Because S equals 0 is not allowed. Otherwise, I cannot write divided by S. I can say directly that that is 1, even though I didn't write, but S cannot equal 0. Otherwise, I cannot define the same thing. Now, the calculations is not so difficult. I will plug in also the transfer function of the model, which I gave you exactly at the beginning. And look, proceeding with the calculation. If the calculations are not clear, please say to me, because the calculation should be done at the exam. What I am doing probably from here to here, I am multiplying numerator and denominator by Sn plus b. This means we have an Sm plus b in the numerator, and I have an Sm plus b here instead of 1, and then I will cancel this denominator. I don't know if it's clear what I did from this to here. I think so, no? It's math from gymnasium. I have a binomial expression, S multiply M plus B, and a binomial, a monomial expression, excuse me. Polynomial first order, no, excuse me. We can follow me, no? You can follow me. I multiply by S multiply M plus B, numerator is denominator. I have this expression here, and I cancel. This must be done in the exam. It's gymnasium, I think. No? Then look, we can directly calculate the limit, because for S equals 0, this will disappear, this will disappear. I assumed, we will discuss this assumption, we can see here a little bit later, that GC of S for S equals 0 is equal to 1. In any case, please assume it not 0. Then we will see this implies something in the choice of the controller, but it's not a conservative assumption. We can manage. And then we can see that this is not 0, because B is not 0, is the friction parameter is physically there because of the losses which I have. Think 1 second. Question here. This is important because the calculation must be done. We can see that H equals 0 is not enough, because the idea was this. Calculate this limit here in this form here, but the specification was 0. You remember in the first page. This limit here must be 0 for some H. Now I use the theorem because you can see how easy, let me say, is to do this calculation. Gymnasium. Of course, we have to have the concept of the transfer function, Laplace, but anyway, we are here at the university. But the advantage, if the system is linear, please pay attention. If the system is linear, or if you have a linearized system, I will tell you a little bit later, but not relevant for the exam, but just to know. We don't need to calculate E of t. Do you remember the differential equations in dynamical system? Oh, dynamical system was heavy. This method, free answer, for answer, and then when it's non-linear, Lyapunov. So we don't care about E of t. We work in S, but must be linear. Sometimes this error I found also for engineering already expect must be linear or linearized, or let me say almost linear. But if you have almost linear, we have an approximation. Also in the linearization, we have an approximation. But nevertheless, in the approximation, we can estimate the error. Taylor, remember, I tell you very quickly. Okay, now, if zero integral is not enough, we will try with one integral. This means now we consider h equal 1. We proceed from 0 because h belongs to n. No? It's a natural number. Here in this course is a natural number. Yanis, my PhD student, he is working with h real. This means half integral, a quarter of integral. Here we have one integral, two integral, three integral, four integrals. Makes sense, no? Integral to 2 times, what is the meaning of twice integrals? If I have the acceleration, the position is twice integrals of the acceleration, right? In order to understand what is the meaning of 2 times integral. But what is the meaning of s up to 1 divided 2? Half integral. This is really difficult. But we do with Yanis, not only with Yanis, with another PhD, applications in which we applied half integral. This idea was for a mathematician here from Lüneburg, Riemann, is no integral of Riemann. Look in Google. Riemann integral, fractional derivative. Fractional derivatives. Basically, the derivative of the integrals, not integer. Integer means one integral, two integrals, three integrals, so on. And we can understand the acceleration, between acceleration position, we have two integrals. But what is the meaning of 1.5 integral? Extremely abstract. Did you find Riemann? Dannenberg, yeah?
Yeah.
Dannenberg. Did you find fractional derivatives? Of course. Integral of Riemann is clear. Fractional derivatives, if you add the keyword, you can find something. Now it doesn't matter. Just to understand that what I am telling you is somehow
Derivative or integral?
an integral is also a derivative in terms of fractional. In terms of fractional. Beta probably fractional derivative is most used. Okay, calculation now, quickly. Calculation. Now the calculation we learned. Did you find something fractional? Yeah. It's here from Dannenberg. Dannenberg is een verloren ort. We can say it. Yeah. It's a little bit offensive, this, no, if I say it's a little bit outside of, no? Isolated. It's a small village or how? Okay, doesn't matter. I don't want to say something inconvenient. I don't know if somebody from Dannenberg, but Riemann was from Dannenberg. This is but also Leonardo da Vinci. Vinci is a small village trio that we say in a calf village. And Vinci is in a calf, but Leonardo was born in this calf. But the calf in Italy, the people that they say calf, the people that he wants in the city. I mean, I come from a calf. It's very, very small. Calf, you understand calf?
Yeah, we say it in German.
Okay. Yeah, we say a little bit different, but the word is, the root is, we can recognize. But it's, in our case, it's not so nice. Besonders for the people who's living there.
Yeah. I think in German too.
Kafoni. Is not so nice to say. But the people say to us, these people live in the city, and say that we are okay. It doesn't matter, but this is the classical dialectic, I would like to say, relationship between people who is live in the town and live in the highway, no, in the country. Okay, look at this calculation. Now we are able to do, I will copy again this expression here after simplifying S and S. I don't know if you remember. It's exactly this here. This remain the same because S, but we have here S here, because H is equal 1. I mean, the same, but I have here S. The same like here, the same like here, but we have S because H is equal 1. Now, if you do the same procedure as before, if you multiply numerator and denominator by S and S multiply M plus B, this block here, we have this expression here instead of this one. I'm asking you, from here to here is clear? Ginage. No? Now we can see because of the presence of this S here, the limit is 0. In accordance with the theory which I told you, which I also demonstrated in the lecture, we are sure that we will achieve the error equals 0 in infinite time. Can be used, because the reality helps us because what we did in the modeling is a simplification of the reality. This I told you a lot in dynamical systems. Because really we have a static friction. When the force is not enough to overcome the static friction, I will stop. It's clear, no? This. Okay, ready. Go ahead. Second specification. Yeah, second specification. But before saying the second specification, look. We have here Ki divided S, multiply this. Why we have it divided S? Because we calculated as H equal 1. For our goal, for our system, H equal 1. But now, if you look at this scheme here, we have here Ki divided S, multiply GC of S. But if you multiply these two blocks, you remember this GOL, open loop or the loop gain, open loop gain, different with the notation. Now, this GOL, let me say open loop gain. In some books, loop gain, because it's when I loop, is exactly the same as we had in the position control. Because you remember in the position control, we achieved the goal which H equals 0. But S was here. Because again, the position, if I have the position is the integral of the velocity. This means we will see that starting from now, the calculations are the same. Structure the same. Of course, in the exam, I will change a little bit the value. No? But structurally, we don't have to we have just to learn one method. Of course, if I will ask an acceleration control, you have to be careful, but I don't ask. Acceleration control we can do. We need two integrals. Just you can intuitively understand now. For acceleration control means torque control, two integrals. Difficult, but I don't do because we didn't do it. But believe me, is once you learn this, you understand it is easy to do. But believe me, position on velocity control. Why that? Because I will pretend or I will ask what I did. It could be that in this folder you can find force control, which is an acceleration control. Force control is acceleration control, but read, but I don't do. We don't find in the examination, but it's there. I think there is a force control. If you want to look, but just for curiosity. Okay. Now, look at this. Look at the scheme here. Do you remember we have a signal of the position control? It's the same concept. Because until now I told you that I would like to achieve 10 meter per second, but I didn't say how much time I have to I need or I want to consider in order to achieve this goal. This also is important control because if I want to achieve 10 meter per second in 100 here, this means I will not move much. You remember last time I told you the problem was to move from a position 0 to 1 meter. You remember? The procedure was the same, but the second question was I would like to achieve 1 meter in, I don't remember, 1 second, half second, and so on. Here is the problem is the same. We have a goal, it must be achieved in, let me say, in a reasonable time. Because until now, I didn't tell you about how much time I need. I mean, it seems to be infinite time. what is enough to say infinite time? So infinite time for us doesn't mean anything. Means somewhere. You understand somewhere? Auf Deutsch wäre irgendwann. Of course, irgendwann doesn't make sense in the practical life. No? I would like to achieve this velocity, 10 meters per second. It seems to be, what I wrote here, in 2 seconds. No? Seems to be. Of course, this is a simplification because I am assuming, using this scheme, that the velocity change over time, the velocity v of t change over time linearly. This is not true. Do you remember in the course, it's not valid. In the course of last semester, dynamical system, we have seen that we are always an exponent function in linear system. Do you remember? Always an exponent function. This means, but we can approximate in the first part of the exponential function as in a linear. But if it's not possible to approximate, we will see we can use nevertheless somehow. I show you how. I show you how. But I would like to say we can use any possible approximation. Look, I would like to achieve 10 meters per second in 2 seconds, assuming that I will have a velocity as a linear form velocity, exactly as in the picture. This means if I consider now R of t, let me see what I put here. Basically, the change, or better to say, R of t in our case is the velocity. How change the velocity, as I told you. Better to say how change the velocity is. We can see that yeah, it's in the time. If this factor here is an acceleration, we can see that the R of t is basically how changes our velocity. I mean, you can see a little bit of mismatch of notation, but I intended that R of t is valid between 0 and 2 seconds, just to understand. And then, of course, we have this. I will clarify a little bit later. I mean, V of t, better to say, is the red line, which is not exactly R of t, because R of t, we will see, is our reference signal, which can be used in order to approximate. Please pay attention. We can see from here in order to approximate my real velocity. Again, V of t, if you want, I can write in red. If I find but otherwise I can say it's exactly what basically we have in the reality, something exponential, which for a small period of time can be also seen in a possible ramp. This is the reference. This could be nice if I find quickly. Red color, but it's fine here. Thank you. I'm sure. In any case, R of t is what I want to follow, because the idea is to achieve the goal within 2 seconds. This means I can approximate there, and I don't find it to say the red color, which is V of t here, or the better to say, I would like to approximate the R of t with a particular red color function, which must be calculated using Ki. In fact, the question, the exam, looks something like that. I will not put this picture, but I will put exactly this. And of course, I will show you now how we can answer the question. Believe me, easy enough. Let me show you why this is enough. Is this enough? Let me read again. I don't know. It could be, I mean, it could be that I give you directly this, easier, or I write, please pay attention now, 10 seconds, excuse me, 10 meter per second, please pay attention now, 10 meter per second that we can write in 2 seconds. It's clear that the acceleration phi. I don't know if you can see that. If I write, for instance, the exam, 10 meter per second in 1 second, what is the acceleration? 10. Is difficult the exam? It could be that I will give you directly this, but more practically, what we do in the praxis, if I want to achieve 10 meter per second in 10 seconds, what is the acceleration? Assume that I have in a ramp. No, of course. With this structure, it's always so. Of course, if the velocity change, it's not so directly. But anyway, if I directly go the ramp, you don't have to calculate anything. But please pay attention. If I write goal in which time I have the goal, of course, assuming that the velocity change linearly, no? Otherwise this calculation is not valid. Agree, no? If the velocity change randomly, we cannot divide it. But the assumption is always the same, that the velocity changes in a ramp. In fact, look here, no, it's written somewhere, but I will in a ramp, no? Meaning, typically we formulate this kind of problem in this form here. We have to calculate Ki such that the error at T infinite is less than the tolerance. The reason is, to the ramp, no? The reason is that we try to approximate exactly this scenario here, this situation, but we have to be aware that with one integral, we will, for a system of our system, let me say quickly, this means for a system which has just a pole in the origin, this type of system, I didn't tell you much, will never achieve exactly the ramp. We will achieve the ramp, but with a bias. This I didn't tell you much, but in any case, in the exam, I will consider such kind of tolerance because it is not possible to achieve for our system, for the type of our system, exactly the ramp. But for us, it's not so important, we will see, because first of all, it's an approximation. And we don't want to implement many integrals, no? As I told you. This means we can nevertheless approximate our goal with this method here. Let me tell you something more, and then we will do these easy calculations. Is as if I will calculate an Ki that in a relative short time, I will achieve steady state, or the almost steady state, the goal. No? But the goal is achievable now because it's less than. No? It's less than, it's not equal. Let me show you the calculation. The risk, and then we will see later, and then we'll have an overshoot, but we try to correct. The calculation is extremely easy now because it's similar as before. Please consider this S here. No? This must be considered now because S allows to achieve the steady state error, which we want. And now we have to calculate Ki, which is here. It's clear how this phi come from, or where this phi come from. Yeah? It could be that I will say, assume that in a linear velocity, I will achieve 10 meters per second in 10 seconds. This parameter is 1. Assuming that the variation of the velocity change linearly. This is an assumption. Change linearly means acceleration constant. Now, this calculation is easy. No? S and S we have seen before, but why I am writing here S squared, phi divided S squared? You can find also this in the data sheet because the Laplace transform of a ramp is 1 divided S squared. You remember the Laplace transform of a step is 1 divided S. Unit step. If I have a 10, of course, you have to multiply by 10 because the Laplace is in a linear transformation. Also here, I will write for you that the Laplace for t is 1 divided S squared. I have to just to multiply by phi because the Laplace transformation is in a linear transformation. This means it's an integral. This means I have to multiply by phi. Phi divided S squared is exactly the Laplace transform of this ramp. Now, S and S squared I can cancel. I mean, I remain an S here. And if you do this calculation, gymnasium calculation, if I multiply S before by S parenthesis S multiply M plus P parenthesis, numerator is denominator, of course, multiply here, I will obtain this expression. And now I can cancel again S and S. I don't know if it's visible. If I multiply again by S, which multiply this monomial expression, I will have in the numerator something like that. Instead of 1, I will have this one, as I did before. And now S and S can be cancelled. And for S equals 0, or that tends to 0, we'll have this. Now, if you consider this must be or that should be less, this expression, excuse me, this expression. Again, here, from here to here, I multiply, probably you didn't see, no? From here to here, I multiply by S, which multiply parenthesis M, multiply S plus B, parenthesis. This S I can cancel with this S here. Instead of 1, I have this 1, because I multiply numerator, denominator. For S equals 0, from here I will obtain this. But now, you remember the specification. The error, which is this one, the error, which is this one, must be less than something which approximate well the ramp. Please, the concept is here, but I am writing in infinite time. Here is not the case. But of course, for us, infinite is just a way to say long time. It's long time. Very often, in fact, we exaggerate with this in order to obtain, nevertheless, an approximation, a relatively good approximation in a relatively short time. I mean, infinite for us doesn't mean anything. Could be also 2-second infinite. It depends. Anyway, if this must be less than something, 10 of minus 6, if it is less than 10 of 6, it's clear that Ki must be larger than pi multiply B, the friction, multiply 10 up to 6. Of course, it remains valid. It remains valid that is less than this in infinite time. It's a large time. Therefore, very often we write a very small value, such that also for a short time we have nevertheless and a good approximation on our goal. But this is an approximation. It is an approximation. But believe me, our system will follow my ramp with a bias because the type 1, I think is with 1 0 in the origin, will never achieve the ramp, but will be in a ramp, but with respect to the reference with a bias. This means if you have a very large Ki, it could be that really we obtain a good approximation. But the risk now is that we have an overshoot. You remember the red color curves. We have an overshoot means I probably have the picture now. No? Now I show you now the picture what I intend. Here's the calculation. Of course, this is a theoretical calculation. Probably in the real cases we have a less more than 10 up to minus 6. We have to be careful with this value because really it's not possible to realize such kind of gain. This is practical. Yeah, we have value which is not so large. But just for the exam, it is easy is in the sense it's easy to understand. Okay, here I told you already. We can see that Ki is directly, just to comment, is directly a function of our acceleration, our friction, and our specification. Makes sense, no? Makes sense. I have to push energy, but of course, this is really something theoretical, no? But just to understand, this is important to understand. It's a function of the acceleration. If I want accelerate more higher acceleration, higher gain, our Ki. And if I have larger losses, of course, I have to put more energy. And of course, if the specification is very strong, typically 10 of minus 6 is just to do the exam. That is really 10 of minus 2, 10 of minus 1. Believe me, it's not so. But just to show you a little bit, think about 10 of minus 1. Makes more sense. Or 10 of minus 2. This means, excuse me, 10 of 1, 10, if the specification instead of 10 of minus 6 is 10 of minus 2, we have here 10 up to 2. Just to understand, should be also possible, no? Should be possible this realization. Okay, but just here more to work conceptually. I would like to conclude with the control, and then we can discuss. We can take the rest a little bit. We can go to Mensa if you want, but I would like to complete this. Now, let me see. It's not long, believe me, it's not long. Just 3 slides. Look what happens now, or what could happen. Fix the idea. The idea is, if I approximate very well, you can see here, nevertheless well, you can see that somehow recall as our ramp. Like, it's a shame we don't have time, we didn't have time to show you in Simulink, MATLAB, otherwise the idea with Simulink MATLAB, we can simulate also real system, Ki, not so big, but in any case, we can really see that also for Ki not extremely big, we have some possible overshoot. Because the ramp is calculated or is conceived for T infinite. We break this. This is the problem, no? Really, please pay attention. We apply the step, no? To apply the step, but we design the controller considering Ki related to the ramp. This means we will follow the ramp, but we will break thanks to this signal, which is limited. I don't know if it's clear. This R of T is a design signal, which is not applied. The step is applied. I mean, you push and you accelerate. The throttle wheel moves depending of Yeah, I think so. We fix, you look and you tackle, you fix, you go. For the system, this is a step. But KI is already fixed in your intelligent unit control system in the car. This is done basically once when we design the control. As age, if we have age, we don't have age, it's fixed before that the car and the car runs. Now, when we have a 10 or we have a 20, we have something like that. It doesn't matter if it's 20 meters per second or it's 10 or the 20 meters per second. This overshoot will be in a percentage of my goal. We will see now. It could be that it's not acceptable because you have something like that, an oscillation in the acceleration, in the, excuse me, velocity, also in the acceleration. It could be not acceptable. Here it's not so dramatic as in the auto park. The auto park risk to crash again the wall. Now do you remember this? Here, nevertheless, in the train and the auto, this kind of, excuse me if I mimic, this kind of oscillation could be not comfortable, but also for also a safety reason. If you exceed this velocity, you can be fined by policies, or anyway, it's not suitable. Nevertheless, let me show one, three slides, two and a half. This is the controller which at this moment we have. Of course, 10 over 6, I told you, just theoretically, just to put a value. Typically, is much less. But it also depends which kind of system we have, or which kinds of power we have at disposition. Because this is reflect the power, because should overcome, should guarantee the acceleration. This element here, please pay attention. I told you here why I put this. This is not relevant for the exam, but to understand why I try to comment here. Depends of the acceleration, depends of the losses, depends of the specification. It's the power. Of course, specification in 10 up to minus 9, of course, we have more power. Its acceleration instead of 5 is 10, more power. If the losses is 250, more power to achieve the goal in 2 seconds. Look at this. I will do some specification. Which one? The most important is this. This is the overshoot. What is the overshoot? Is here. 0.1 is the percentual of 10. This means 10%. This means should be not more than 1 meter per second, the error, the maximal error. Why that? Because I give you in the exam. But practically means it's not acceptable as an error more than 10%. Why I am speaking about 10%? Because should be valid also if the velocity is 20 meters per second, 50 meters per second. This is a specification sometimes also. You know that I worked with Volkswagen before coming here at the Leuphana in Westphalia University Applied Sciences with project with Volkswagen. The specification basically came from Volkswagen in accordance the precision which you want to obtain, the controller and so on. But of course, in the auto park this is more clear, because the sensor give the distance 1 meter, the wall, or 1 meter, let me say, in 10 centimeter. And of course, the error must not be more than 10%. Anyway, we can calculate what is acceptable. In our case, in the exam, could be 0.1, please pay attention, could be 0. This means no overshoot. No overshoot means, remember, I told you last time, it is going, we approximate, and last time was the wall. The wall is the reference without oscillation. Of course, the reference typically for safety reason is calculated, let me say, before the war. And then we will give the tolerance. Now, next week, I will tell you a little bit about these two equations, where they come from, but very quickly, because I give you in the exam these two equations. Here is more understandable because we have the maximal, the peak is 1 plus S hat, also in percentual. This means applied here, this means the peak is 10 plus 1, right? If this is in percentual. I will tell you a little bit where this comes from, but it's not necessary for the exam to know exactly. But just at this moment, I didn't have time. We concentrate on the calculations. They are approximating equation. In particular, this is extremely important because this I would like to emphasize again. This equation here transfer the specification on the maximal overshoot of the closed loop system. This means of the controlled system. What we want to have, basically, this function here, this V of t, is the result, the answer of the controlled system. We want to obtain this error, possibly maintaining maximal this error, maintaining 2 second, let me say more or less the goal, or to achieve the goal in 2 seconds. We will discuss it a little bit later. And this means this equation here transfer my closed loop specification, which are here, with, you remember, the phase margin of the GOL. GOL is the open loop function, thanks to the Bode theorem. I will go ahead and then we will come back probably in the second part of the lecture. Look, if I apply the equation, this value without thinking where they come from, but I will give you some hints next week, I will obtain with the calculator that the phase margin, now we'll tell you about the phase margin. What is the phase margin? Do you remember last time? It's the difference between the margin of a GOL loop gain or the open loop gain, a better loop gain than I like, and minus 180. Because do you remember, minus 180, this cross frequency is the critical frequency, which must be avoided in any case, or let me say must be not overcome. And not only, we have to guarantee the margin with respect to this frequency, because the Bode theorem is not only a measure of the stability, but is a measure of the oscillation. Therefore, M phi phase margin. I will come back to this with the diagram. This calculation, I think, is clear. We have in radiant, I will tell you next time. You have to remember that in radiant. M phi is in radiant. It is not easy to remember because you have an arcotangent. Typically, everything is in radiant. Not typically, must be in radiant. And I can transform this 0.69 radiant into grad. This is easy, no? Because I have to divide by pi and multiply by 180. Do you remember this transformation? Because then we will use table in grad. Between radians and grad is easy, no? If you have a gradient, you have to divide by pi and multiply by 180, and you transform in grad. Now again, this GOL, this is GOL. Now we calculate the phase of GOL. Open loop gain, loop gain. function, which is the product between GR, the controller, and GV, we call GV, no? The transfer function of the system. Yeah, we can see. Here I put also the value, no? This is GR, this is GV, with the value which I gave you at the beginning. The mass was 1,000 kilo, and B was 25. We already used this value, or at least this we used, B. This is the control, no? Until now. The GOL is the product. If you loop, I don't know if this is clear. It's easy to remember. Open loop, no? Or loop gain. Loop gain means you loop and you find this, multiply this. Open loop you can say also, because if you open, the transfer function is nevertheless this multiply this. You can say as you want. Loop gain, if you loop, you find this and this. If you open the loop, the transfer function is, anyway, it's the controller multiply this. I would like to say loop gain. This is what we have at this moment. What do you have at this moment? Look, calculating omega g, this critical frequency of omega, in which the amplitude is equal 1. Should I repeat the theoretical part of this? Should I show you why it's important to understand a little bit these fuzz margins? I open just one slide, so we can repeat a little bit. This empirical equation where we discuss next one, you don't have to learn the meaning in the exam, but I would like to tell you a little bit, because otherwise it seems that I invented it. In the literature is a good approximation, because otherwise you have to use really computers or tables and so on. Let me open the slide. Goal is to design GC of S. Goal is to design GC of S. Before, in order to design GC of S, we have to calculate, let me say, what we have with the GOL, because GC of S will correct eventually if GOL does not respect this specification of the overshoot. I didn't have time, but we can also consider more complex controller in which we can balance the overshoot and the, let me say, rise time. What is the rise time? Exactly what we did with KI. With KI, we try to approximate the rise time, the rise time, the time which I need to achieve the goal. But we didn't have time to analyze the other part. Therefore, I have just here a little bit this specification. But once we learned this, the rest is not so difficult. Let me open now one slide of the past lecture. I would look here. Let me look. I think a little bit boring, but we are almost ready, no? Then we take a rest, then we do the aerostat system. But I would like to compare with the results of last time. Okay. Where is now? Yeah. Okay, found it. The question, no? Extract. I don't find it. It's not here. Strange. Oh, I'm not able to find this now. Should be this. Well, I don't find the PDF. Hmm. But I uploaded it. Oh, unbelievable. I have to download from my study, but I don't find it. Okay, let me see if I find it in another folder. 1 second. To measure the mix, like the same. PDF signal. I don't find a PDF. Did you see a PDF? I have to compile again. Cannot be. Oh, I don't understand why I don't find the PDF. Let me. I'm sure that the PDF file disappeared. Okay, let me see if I am able to. Can you help me? Yeah, can you help me? Okay, I found it. I found it, but it's strange that disappeared. The idea, and then we will conclude. No? It's not far away, the conclusion. And everything started from here. Do you remember? If you look at the denominator of these all transfer functions, in particular, now I would like to remember you why the goal isn't a disturbance. If you look at this scheme here, which I consider the disturbance, in the exam, you don't have the disturbance, believe me, forget it. But we have a goal, which is similar to the disturbance. Look, the transfer function of y, let me say, between d and y, or if you want, between y and d, you can say as you want, with the goal to 0 is this one, which is the same if the disturbance is 0, if you consider the transfer function between the error and the goal, as I told you before, it's exactly the same. Exactly the same, numerator and denominator. Therefore, I told you we can consider the goal as the disturbance. But if you think also in other ways, if you have a goal, you have to do something that disturb. If you have a less goal, not so disturbed. Okay. Now, we can see that all these transfer functions, they have the same denominator. This means given, let me say, a control system or in a control loop and scheme, something like that. Of course, what is important for us, you remember in high school, just trivializing the concept, that the denominator is not 0. I mean, here I am considering the critical condition of the control loop. You remember in high school we learned if the denominator is 0, we cannot do anything. Fix this. You understand also the reason. But at this moment, go ahead. This condition here for functions which are defined in a complex variable S means that can be written in two conditions. I don't know if you remember the lecture of Benedict, of Mare, magnitude equal 1 and phase minus 180. These two conditions are, or better to say, are equivalent to this one. Because you remember, in a complex value, have an amplitude and the phase. Now, we don't have exactly a complex value, but we have complex values because we have complex functions. Just a little bit to go ahead. Now we can see that we can define possible critical conditions. We have an important theorem, which is the theorem of Bode stability, which exactly try to quantify how critical is our control loop, considering just the open loop system or the open loop structure, GOL. Moreover, this Bode stability criterion does not consider S, but just omega. This means this analysis in steady state, you remember steady state by Mare, this means we consider S equal J omega. Do you remember this? Without the real part of the S variable. This means when the transient is already passed. The theorem is extremely strong because the theorem say, I will comment the theorem using this scheme here. The theorem say if this critical frequency, omega g, sometimes crossover frequency. At this crossover frequency, which is the frequency in which the amplitude of GOL equal 1, the phase margin is 0 or less than 0, we have the system which is unstable. This means to obtain asymptotical stability, the theorem say that we need the margin more than 100. Let me say we have to be larger than minus 100 or minus 180. This means positive phase margin. Let me comment a little bit more. But in any case, this theorem measure also the level of the stability. Because you remember last time I told you when we are close to this critical condition, the system becomes to be oscillating. I didn't specify many things about that, but this is the idea. It's a theorem I didn't demonstrate, but it's extremely strong. Yeah, because fixed, starting from the specification of the closed loop system, let me say also in time, transfer this specification into GOL in frequency. Better to say steady state. Let me see concretely, practically. We didn't invest many time in energy or yeah to demonstrate or the energy to demonstrate this. Look, this allows me to calculate this omega g crossover frequency in some lecture too, or this is nevertheless the critical frequency when the amplitude is equal 1. Practically means this. Is the amplitude is equal 1, and I will come back with a negative signal because of the inversion of the, or let me say, yeah, we can interpret this all. I will add continuous signal, and of course, this is in a critical situation because generates nevertheless instability. I mean, we can see that theoretically we have a plus, minus, plus, minus. If this minus becomes plus because of a phase delay, because of the phase delays, this phase delays, this minus exceed the condition which I told you, we add to the loop is intuitive interpretation. Large and larger signals. And this is the meaning a little bit. Let me calculate omega g. You have to solve this equation here. Again, everything in steady state. Instead of S, I will put J omega G, which must be calculated with the constraint equal 1. Equal 1. If you calculate the amplitude of this signal here, or this system here, excuse me, we have the amplitude of this is exactly this without J, because the magnitude of J is 1. You remember, J is root of minus 1. The amplitude is 1. Is this clear? The amplitude of the constant is the constant itself, the amplitude omega g is itself. But here we have a j. J is an imaginary part. What is the amplitude of j? Root of real part square, which is 0, plus imaginary part square, which is 1 square. This means it's 1. I don't have to put anything. Here I have to put something because the amplitude of 1 is 1, divided root of real part square, 25 square, is here, plus this part here square. Think about 1 second. Now, to calculate omega g, if you have the calculator, you can do directly. You can calculate probably if you have a calculator which you can program. But if you don't have, it's not so difficult because look, you can write in this form from Gymnasium. Then if you square this part and this part here, you have this equation here, which is an equation in a polynomial of order 4. You remember I told you last time the possible idea is to consider omega g square equals omega tilde. You remember this? Because we have in particular polynomial expression, no? Which we have a variable up to 4, the variable up to 2, as the variable up to 0. No? If you want, you can use this trick, and then you can use the Pico formula. But there is a way more direct. Look, I consider dominant this omega g up to 4 respect to 25 omega g up to 2. Now, of course, this should be verified later, but very often could be also approximated. I mean, in particular, if omega g is relatively large, as we expected, but in any case, we have a 10 up to 6 in this case, but of course, 10 up to 6, not necessarily there. No? This means the hypothesis large enough omega as is written, but can be used, Then, of course, this is an approximating method. We have at the end this here. This is easy to calculate now. No? Omega g squared is equal to this one. And then I have to calculate again the root. This is the critical omega g, in which we have the amplitude equal 1, more or less, no, approximated. What I am doing now, I have to calculate what happens in terms of phase at omega g, because as I told you, the condition, at least I have to obtain a phase less or more, if you think about the negative value, more than minus 180, for instance, minus 160. How much I have to have? We calculate it. This phase margin. Oh, I lost everything. I need the phase margin 55. This means minus 180 plus 55. This is a little bit more than 120, and 125. This is what I need, because I need an overshoot not more than 10%. In accordance with this approximated equation, which I will clarify a little bit next time, where it comes from. And now we have to look what we have with the controller, which at this moment we have implemented. This means I do these calculations, the phase of my GOL calculated at J omega G. Omega G is exactly what I calculate now, when the amplitude is equal 1, in accordance with the Bode theorem, which came from this idea that the denominator should be not 0, or better to say, not 0 with the margin. Because of course, I didn't have time to show you for phase margin smaller, the system will be oscillating and more oscillating. Believe me, we didn't have time to do the Laplace transform, back Laplace transform and so on. But look now, the phase of this number, complex number, because this omega g is in a value, minus the phase of this complex number. Why that? Because GOLJ omega is this one. If I go up and down, is this one instead of S J omega. J omega, yeah, at this moment we don't have here, but we have here, excuse me, GOL, excuse me, GOL, J omega here, J omega here, J omega here, and in particular J omega G. This omega G we have. You have to calculate the phase of the GOL in accordance with the Bode theorem, which says, which connected the closed loop conditions specification to the GOL steady state because of the J omega G. Look, if I put why this is clear, no? Because is the denominator. No? You remember this, we can demonstrate if you write the complex number in exponential number. I don't know if you remember this. If you don't remember, in any case, this is in the data sheet. No? The phase of a complex number, numerator in a complex number, denominator in another complex number is the phase of the numerator minus the phase of the denominator. Probably we did with Mare or the math. Is this enough to transfer this form in exponential function? I don't have time to redo math one, but it's in the form example. If you have an A plus JB divided C plus D plus JD, phase of this is the phase of the numerator minus the phase of the denominator. If you have the product, is the sum. We can demonstrate with the with an algebra of the complex number. Look, we have the phase of this. I have to put omega g, but look, why minus pi divided 2? Because we have the phase, basically here is a constant, 130, 10 up to 6 divided omega j is the value. Did you agree? Divided j. But the phase of 1 divided positive, 1 divided j is the phase of a constant divided j is minus pi divided 2. You remember this in the calculation of a complex number. It doesn't matter which value I will, important is positive, no? The phase of j is pi divided 2, but the phase of 1 divided j is minus pi divided 2. Did you remember this from math? Because it's the phase of the constant in the numerator, which is 0, minus the phase of j. But the phase of j is minus pi divided 2. I don't know if this is clear. Should I calculate for you what I intend? You are good in math. I show you. Please pay attention. Constant, but positive. The constant is positive. Divided j. It doesn't matter which kind of constant. Do you remember now? I don't have time to demonstrate this. But if you look at the notes in math, you can remember this, or you can recall this. Is the difference of the phase of numerator, the phase of the denominator. Because you can express the complex number in exponential form, and so any way to show. The phase of this is 0 if this is constant, positive. The phase of j is pi divided 2. Practically, do you remember this? Imaginary, real, you can see directly so. This vector in this position at the phase pi divided. I will show you a little bit better what I intend with the calculation of the rest of the phase. Now it's clear why it's minus pi divided 2. Then why this one? Because I have to calculate the phase of this. It's the arctangent of the imaginary part divided the real part. You remember the phase of a complex number. Like here we can say theoretically, why this is pi divided 2? Because it's the phase of the imaginary part divided the real part. But the real part here tends to 0. And then the arctangent is pi divided 2. If you remember a little bit in the trigonometry, you remember this a little bit. No? When the real part is going to 0, we have this effect. Let's look a little bit in math, but anyway, I will put in the data sheet. We are not for math. You already did math. And you have to calculate this arctangent with the calculator, 90s or minus 90s. And then you can transfer directly from radian to grads. And we have more or less minus 180. This means we don't have margins. a very critical situation we have. The reason is that ki probably is too large, but we don't change now ki. We don't change now ki. What about the regulator? We need a regulator, and I will give you this equation in the exam. I give you this. I mean, I would like to control the system. I would like to correct, better to say, or to improve the controller using a GC of S of this structure here. I will give you this. We can see that the original hypothesis, GC of 0 equal 1, is guaranteed with this structure here. You remember this? I told you. Assuming that, and then we will verify later if this can be done or not. We can see that with this kind of controller, we can achieve the goal, and the assumption at the beginning is respected, because for S equals 0 is 1. You remember, this was in a point, an open question, open point. This means I have two guarantees that this part of the controller at omega g, which we calculated before, this critical frequency or crossover frequency and so on, must be at least 55 degrees. Then I have to calculate with the specification tau and lambda. How I can do? Table. I think the table is already my study, right? I upload the table. I show you which table I intend. I think I uploaded it. No? Yeah, this one. Let me. There is in my study. I mean, in the lecture is there, no? But I don't know if I uploaded extra. 1 second. I will almost ready really. I will just to read the table. You can see here this approximating at the end of this lecture. Do you remember last time this approximating equations? We have also a different approximating equation, but this we didn't do. I didn't tell you about the specification in the rising time because I don't have time. But once we understand or understood this lead structure, yeah, of course, we have another controller which with the name is lag, which can be used to correct or to manage also the rising time and so on. But about this first part, I didn't have time to tell you. Because of course, if you combine both and lead and lag, of course, you have more possibility to obtain the required overshoot without destroying or renounce too much on the rising time, which at this moment we asset or we perform or we calculate with this ki. No? Look, you can use this. I think I will. I don't remember which. Probably this one is better to read. I don't know if it's better. If I print, probably yes. We are using a lead. Forget this. But basically, is the lead with a minus. Here we have just the phase. Basically, what is this graph? Is the, we can see here, arctangent of this lead for S equal J omega, parameterized by lambda. We can do with the computer, but you cannot use the computer. You have to use this picture. I will give you this picture. As a function on omega t or omega tau. In our notation, t capitalized is tau. No? We can build this in a function. Arcotangent is not a bad function, a continuous function, infinite times derivative. If you have a computer which allows to build it for different lambda, parameterized in lambda, you can understand that I can build with MATLAB. It's very easy. MATLAB has already this in the toolbox inside. Now, look, very, very important now. Look at here. We need 55. Did you agree? 55 phase margin. This controller, this transfer function, this is a transfer function, not the whole controller, but a part of the control. In our case, this k is equal 1. Also here, don't influences the phase, because if k is positive, here is not specified, but is positive, does not influence the phase. You remember the constant. Remember this concept, the concept here. The phase of k is 0. This means if you calculate the phase of this, the phase of 0 plus the phase of the rest, which we have in our case. Now, if you look here at 55, please consider the point in which we have the maximum. You remember I clarified why the maximum, because we did a lot of approximation. Everything is approximated. But in the maximum, the approximated is not so heavy, because even though we move a little bit in the calculation omega g, more or less remain the same, the phase. Very important is the phase, must be not less than 55. Here, I read what I read at that time. Let me see what I read. Lambda equal 10. I show you now if it's, I don't know. Yeah, it makes sense. Look, more or less, look here, 55 in the maximum, we have lambda equal 10. Of course, we can consider also different lambda 12,5, lambda 16, lambda 20. But why 10? Because we are looking for the maximum. 5 minutes. You have.
I have appointment at 12:30 where I have to pick up something.
Yeah, in any case, it's everything the recording. We need
Okay.
1 second.
Okay.
In the maximum, because we don't have, I mean, it's more robust. The sensibility is something important in our concept. Then if I go in our structure, if I go down, probably it's better to use this to go down for 10. It seems to be that omega t or the tau is 3. 1, 2, 3, 4. No, 3. I think it's 3. It's 3. Yeah. 1 second, then we are closing. It's 3. Omega multiply t, omega multiply t. In our case, it's omega g, because we want to obtain this result at omega g in accordance with the Bode theorem. And then with this equation here, t or the tau, it doesn't matter. I put omega g, I calculate tau. Now I have the controller. This is the part of the controller, including lambda equal 10 and tau or the t equal 0,08. If I put all together, I have this one. Can be approximated somehow? Yeah. I can, for instance, throw away this element here, the unique element, which it seems to be negligible. It could be for omega, not so high at least. But anyway, this is the control. But I can be approximated by PI control. To conclude, this structure here, this GR, is basically similar to, depends on the value is different, to the position controller, but without S. Of course, the value is different because we have a different specification, everything is different, 10 meter per second at the time was 1 meter. But believe me, without this. Why that? With this in principle, internal model principle, that to follow a signal in steady state, we need to replicate the signal in terms of Laplace in the GOL. This means if I want to obtain the step, I have to have 1 divided S in the GOL. It doesn't matter if I have in the controller or in the system. In the case of the position control, we have 1 divided S, or the S in the S in the denominator, in the system, not in the control. Okay, for this part, we can conclude here. If you have force enough, we can meet after the lunch to do another position controller, but we did already last time. But if you have time until 2 o'clock, it could be that we can do that. I record for, but we did also last time in the parking system. I have a similar system with this in aerostat system. It doesn't matter for us. Aerostat car, they are the same. Biological system, everything is the same. Once we have the model, but we did the position. But if you come here, I can do for you.
You would do the same questions you did now for position controller? There's
Yeah.
no more of different.
No, the same as last time,
Alright.
basically. Also today
Mm.
is quite similar, but anyway, we haven't in focus the velocity, but you can realize that the question is always the same. One's oriented in step for velocity, one step for position. Basically, we'll repeat another example as last time in position control. It's exactly the same as last time, but with different value because I have an aerostat instead of a car. But the car is an aerostat. The difference, the car is moving horizontally and the aerostat vertically. If you want, I can do for you. Otherwise, believe me, in the exam, no acceleration control, no torque control, cruise control, velocity control, or auto parking position control. No different cases. Next week, next lesson, I would like to hear your questions, and then I will tell you about linearization outside of the program of the exam, because of course it's not included. You come after lunch or you don't want? Okay. No, it doesn't matter. You come? It doesn't matter. It's already done somehow. No, it's already done.
And then we will do the questions next.
Yeah, this is very important. I suppose on Wednesday,
Okay.
because makes sense, so we have a day to think about it.
Yes.
I will communicate exactly the schedule. It could be that I am at home in the evening, or I am here late in the evening, but I don't know if for you is the going to come here. But if you are here, you have a come also here. But I would like to tell you about also the linearization a little bit at the end, just to inform you. And this approximating, where this approximating equation come from, just flesh out. Thank you for your attention.
Thank you very much.